This last section we need to talk about now is how to make some compounds, and this will be an ongoing discussion, but nomenclature is the ability to name compounds, and this is so important because if you don't know what chemicals you're working on, it can be really tough to deal with. Now, nomenclature in this textbook is split into Chapter 3 and Chapter 4, so we'll kind of do some of it here. We'll keep talking about it as we go through. But anyway, in ordinary chemical reactions, it's usually not the nucleus of the atom that changes, but it's the electrons around it. And there's two types of bonds that can be made. And you can think of these bonds as being the glue that holds electrons together. You can make ions, which is when an electron is actually transferred from one atom to the other. So an ionic bond is usually between a metal, which gives up an electron or electrons, and usually the thing that's accepting the electron or the electrons is going to be the nonmetal. So sodium chloride would be a good example of that. Sodium loses an electron and chlorine gains an electron to make an ionic compound. But on the other hand, there are lots of examples of where molecules share electrons, and those are called molecular or covalent compounds. And they're both really important. Covalent compounds are not as strong generally as ionic bonds, but they can be really useful because life needs a lot of bonds that are acting really fast. Covalent bonds are much more flexible, and so being flexible gives covalent bonds the kick up on life. So most of the things we deal with in life use covalent bonds, but ionic bonds certainly have their use too, and we'll see this as we go through the class. But if you have to make an overall thing, usually ionic means metal plus nonmetal, and usually covalent means nonmetal plus nonmetal, but we'll see exceptions both directions as we go through the class. All of the metals and all of the nonmetals can fall into basically two important categories for us right now. First, we're going to talk about fixed ionic charges. Fixed ionic charge means that the atom always has the same charge, so they're predictable. And there are both nonmetals that are fixed charge and there are metals that are fixed charge. Nonmetals are the easiest because most of them, to figure out their charge, you take the group number and subtract 8 to figure out their ending. And as I've kind of mentioned before, but I'll say formally here, you want to name that anion, that negative ion, with an IDE ending. The metals, on the other hand, there's only a couple types of metals that have fixed charges. And the fixed charge metals fall into group 1A, they fall into group 2A, and they have the stairs. So group 1A would be sodium, potassium, lithium. Those group 1A metals are always going to be +1. Group 2A metals would be calcium, magnesium, strontium, barium. They're always going to be +2. And then the stairs is this funny group on the periodic table. It starts with aluminum, number 13, and goes down to indium, number 49. And you can see it goes left to silver. So it's like you have a single step, 2 steps, and 3 steps. So what this means, the step number represents the charge. So silver is always +1, cadmium and zinc always +2, and indium, gallium, and aluminum always +3. So that's why they're the stairs. +1 in the first step, +2 in the second step, +3 on the third step. Now, the reason why these nonmetals and these metals are important is because they're always going to have the same charge, at least for us in the Chem 200 series. So zinc will always be +2. Sodium in group 1A, always +1. And for example, chlorine in group 7 on the periodic table will be 7 - 8. Chloride, always -1. So the predictability makes this very attractive. So chlorine in group 7A becomes 7 - 8 -1, and it becomes chloride. Oxygen in group 6A becomes oxide, O2-. Phosphorus becomes P-3 phosphide, etc., etc. The main group metals, +1, sodium, +1. Magnesium becomes magnesium, +2. And again, the hip chemist will always know that magnesium is +2 and phosphide is -3 when they're coming together to make bonds. These are the fixed ionic charge metals and nonmetals. What is the probable charge on a barium ion? All right. So what we would do to figure this out, we would see where barium is on the periodic table. Its atomic number, Z, is 56, so that means 56 protons. But important here, barium 56 is in group 2A. It's an alkaline earth metal, and all the alkaline group earth metals in group 2A are going to be positive 2. So we would predict barium to have a positive 2 charge, and 99.9% of the time it is positive 2, just like strontium above it, just like radium below it, stuff like that. They're all positive 2 in that group. All of the other metals, though, on the periodic table, and there's a lot of them, so group all the transition metals except for the stairs, the lanthanides and the actinides, there's some metals under the nonmetals, all of those are variable charge metals. And what that means is that even I, with my PhD, I would not know what the charge is. So we need a way to talk to each other about what the charge is going to be. And chemists use a Roman number to talk about it. So Roman numbers are used with all the lanthanides and actinides, all the non-stairs transition metals, a couple metals under the non-metals, a lot of them. Now, the Roman numerals are on the right there. So Roman numeral 1 is just the I. Roman numeral 2 is like II. 4 and 6 are what people mix up. 4 is IV, and 6 is VI. So just kind of FYI about that, we'll need to use those. So iron plus 2 would be iron Roman numeral 2 like that. That's how you'd write it. Now, you don't write the Roman numerals in formulas, but you would when you're talking about the names, and we'll talk about that. Iron plus 3 would be iron Roman numeral 3, III. Do not use ferrous or ferric nomenclature if you know what that is. If you don't, just ignore what I'm going to say here. Ferrous and ferric is old school and not used as much. Use the Roman numerals. Don't use ferrous and ferric. Likewise, uranium plus 4 would be uranium IV to say it's a 4. Lead 2 plus would be lead 2 II. Lead 4 plus would be IV, etc., etc. So notice if you just said iron, I wouldn't know if it was iron plus 2 or iron plus 3. Or if you said just lead, I wouldn't know if it was lead 2 or lead 4. So the Roman numeral helps us to talk to each other about what the charges are going to be on these things. In addition, there are some combinations of atoms that come together. They're very stable and they have a charge. And these crazy things are called polyatomic ions. Poly means many, many atomed ions. And they're very common. They're more common than some of the other ions we've talked about. So a real common example of this is nitrate. Nitrate has 1 nitrogen, 3 oxygens, and a -1 charge. So nitrate NO3 -1, and sulfate SO4 -2, and hydroxide, another common one, OH -1. You kind of need to sit down and memorize these things. And I hate using the memorize word. I really do dislike using it. But that's kind of what you have to do to knock these out. So on the right-hand side here, I have a list from the Nomenclature Lab, which is the complete list of ions that I kind of want you to think about. And if you can go through and figure these out, you're good to go. Now, there are some patterns. So for example, you can see right in the upper left-hand side, there's a nitrate and a nitrite. And nitrites generally have less oxygen than nitrates. So here's phosphate, PO4 -3. Phosphite has 1 less oxygen, PO3 -3. So there are some kind of patterns like that. But try to go through and figure these out, memorize them. You can make flashcards. I have cheesy flashcard things on the website and the companion you can use. You can use Quizlet if you want to go through that and memorize them. But when you hear nitrate, you need to think NO3 -1. And if you see NO3 -1, you have to think nitrate. So start memorizing those. They will be very helpful to you. So which of these polyatomic ions probably does not contain oxygen? Here's another kind of hint that I can give you. When it comes to those polyatomic names, a lot of them have ATE and ITE endings. And anytime you see ATE or ITE, ATE, ATE, ITE, those almost always mean oxygen. So the only one here which doesn't have ATE and ITE would be cyanide. So we would guess, and guess correctly, that cyanide does not contain oxygen. It doesn't have an ATE or an ITE suffix. So that's one other hint that I can tell you to kind of figure these out. But again, just kind of start going through them, figure out how this works and stuff, and you'll be good to go. You can also learn about my friend Nick the Camel. Nick the Camel Brat ate icky clam for supper in Phoenix. And you're like, what the heck is this all about? Believe it or not, this is a way to help you learn not only the polyatomics, but it can actually help with the acids too. So Nick the Camel Brat ate icky clam supper in Phoenix. Nick has nitrogen, so that's the first letter of the polyatomic ion, and everything else is going to be oxygen. Now notice in Nick you have 3 consonants. Vowels are A, E, I, O, U, sometimes Y. Consonants are everything else. So N, C, and K are consonants. That means that there's going to be 3 oxygens. So 3 consonants means 3 oxygens. And there's 1 vowel. That means the charge is going to be -1. So nitrate, NO3 -1, has 3 consonants, 3 oxygens, 1 vowel, -1, and it begins with N. And this is what sometimes people will use to figure these things out. So you can keep going. Down the neck, kind of close to the bottom, supper begins with S, so that's a sulfur. Has 4 consonants, 4 oxygens, 2 vowels, U and E, -2. Anyway, some people dig this. You don't have to use it, but it is something that's available. Chromate is another one we throw in sometimes, so that's also a possibility. Anyway, if you dig Nick the Camel, cool. If you don't, it's no problem. It's just an option for you to learn. So when you have an ionic compound, you have metals that have lost electrons and nonmetals that have gained electrons. And to make an ionic compound, you have to have equal positive and negative ions. And when you're naming the ionic compounds, it's metal first, followed by the nonmetal IDE ending second. And these aren't usually too bad as long as you know what the respective ions are. So let's say you wanted to add chloride and sodium. Well, chlorine in group 7A gains 1 electron, 7 minus 8 is 1, becomes -1 chloride. And sodium in group 1A likes to lose 1 electron to become sodium plus. So sodium plus Cl minus, +1, -1, charges cancel, NaCl is the formula. Sodium chloride would be the name of that compound. Let's say you wanted to combine calcium and bromine. Well, bromine, like chlorine, is in group 7A, so it's going to be -1 bromide. Calcium, though, is in group 2A. It's a +2 because it's in group 2A. So when you make a neutral compound, 2 and 1, you're going to need 2 minus 1 bromides to cancel the +2 calcium. So calcium bromide CaBr2. You can see how there's no net charges at the end. You could turn the calcium bromide name back into a formula by knowing that calcium's +2, bromide's -1, and you need 2 of them to make a neutral compound. You can do the same thing with polyatomic ions. Nitrate is -1, magnesium's +2. So when you make a neutral compound there, you make MgNO3 magnesium nitrate. Now notice the use of parentheses. If there's more than 1 polyatomic ion, you use parentheses. Otherwise, you never use polyatomic ion, otherwise you never use parentheses. Only if there's more than 1 polyatomic ion. Here's an example of that. Potassium and nitrate would be a +1, -1. That would be written KNO3, potassium nitrate, no parentheses. Only use parentheses if there's more than 1 polyatomic ion. That's really important in chemistry. Here's some more examples. You can have fluoride, which is F-1. You can also, though, use variable charge metals. So here's an example of an iron +3. So you'd write that as iron Roman numeral 3. Now, because iron is +3 and fluoride's -1, you're going to need 3 -1s to cancel that +3. So FeF3 would give you neutral compound, +3, and 3 -1 -3 from the fluorides. You'd call that iron Roman numeral 3 fluoride. You don't put the Roman numeral in the formula. It's only used in the name, just so you know that. Oxygen and aluminum. Aluminum is fixed charge, +3. Oxygen's -2 because it's group 6, 6 - 8 - 2. If you combine those two together, 3 times 2 have a common denominator of 6. So if you want to figure out how many oxygens, common denominator 6 divided by the charge 2, you're going to need 3 oxygens. And 6 divided by charge on aluminum 3 gives you 2 aluminums. So Al2O3, aluminum oxide. Manganese, Roman numeral 4, would be Mn +4, and sulfate, SO4 - 2. You're going to need 2 sulfates to bond with the manganese, so you'd write that Mn parentheses SO4 parentheses 2. That would be manganese 4 sulfate. And again, you need the Roman numeral because manganese is not group 1A, group 2A, or the stairs. All the other metals, you need to use Roman numerals on them. You can also use the polyatomic ion ammonium, which is positive, to react with things. Ammonium chloride would be NH4Cl. Again, no parentheses because we're only using one polyatomic ion. Chemistry.